like in this case, we discussed the sub and inf in the real line here. Okay, so as you can see, the horizontal line is a real line here, and we have a set S. So for this set, we can find the set of the upper bound of the set S. So meaning that for any numbers that is greater than any elements in the set S, we will say that it's the upper bound for this set S. And within this upper bound set, we can find the smallest numbers of it, and we'll call it sub S. If this set is A, then it's sub A. Hopefully you can get that. Okay, so it's the least upper bound of it. And similarly, we can find the lower bound of X, which means the set of lower bound is the collection of all the lower bound of X, right? So any numbers in here is smaller than every element in S. And within this lower bound X, we can find the greatest one here, and we'll call it inf of X. So that's how you can see it. And if we use the more concrete example, which I listed here, let's say that this set is from 0, 1. So this is 0, and this is 1. Okay. So the upper bound of such set, which we denote as U, so U will be, how to put it here? Yeah. So all the numbers in real numbers, and is also greater or equals to X. Okay, so this will be the upper bound of X, and the sub X will be the smallest elements of the upper bound set U, so which is 1 in this case. And of course you can find the inf S equals 0 by following the same way. Cool. Okay. The final part of today's sections is more technical. It's not that interesting. Okay, because I think like in your final exam, you also have to write down a few proof. I should say like a lot of proof. Yeah, so there are not many calculations there. So you don't have to ask, can I bring a calculator to here? It's not useful. So you have to learn how to write down the proof, and this is quite. This is also important when you are doing your research, because how to communicate with others in a very concise way. So you have to learn it. Okay, so basically we have 3 ways to write down a proof. The first one is to write down a direct proof. For example, like the one I put it, like how to prove the rational number is countable. Okay, so that way is a direct proof. It's like given the statement P is right, and how can I like infer that the statement Q is right as well. Okay. And the second way is to do it. It's called by contradictions. So that means maybe I should put it here. So it's more like this one. The goal is to say that if P is right, then Q is right. And now we are trying to prove it by saying that, oh, if Q is wrong, if Q is wrong, if Q is wrong, then it implied P is wrong. But we are given, this is a given condition, P is always right. So that means the contradictions happens. This one is the contradictions. Right. And that means the Q is right. I don't know where to put it, but yeah. So the technique is look like this one. So this is the goal. We want to prove that Q is right as well, given that P is right. But sometimes it's not that easy to use direct proof in this case. So we assume Q is wrong. Assume. Okay? And then based on the assumption Q is wrong, then we figure out P must be wrong. But we are given that P is right, so something weird happens, and that is the contradictions. And by that contradiction, we can argue that the Q has to be right as well. Okay, otherwise P cannot be right. Okay, so that is the idea. Right, and if you have taken the waiver exam, so the first question should you can use the contradictions to prove it. Okay, then is the induction. So this is more like if you can enumerate the things you want to prove. So you will say that, okay, first I will show that P1 is true. Then maybe a few more steps if you want to be more careful or more cautious. Show that P1 is true and P2 is true and P3 is true, and then assume like Pk is true and try to show that Pk plus 1 is true. Okay, and K is any natural numbers here, right? Okay, and finally is some like technical terms here, necessary and sufficient condition. And to be honest with you, like these two terms I was confused by these two terms a lot. So I'm going to show you the graph directly, which is easier for me. Sufficient condition, necessary condition. So these three are this graph represents three conditions here: Sn, Sn, Ss here. Okay, so if let's say that if S is true, then it implied Sn must be true as well, right? So in this case, we will say that Sn is a necessary condition for S. However, if Sn is true, let's say that it happens here. You can imagine there's a point here. Okay, so if you find a point here, you will say that Sn is true. But does that mean S is true? No. Okay, so in this case, you will say that Sn is a necessary condition for S, meaning that if S is true, then Sn must be true, but the reverse may not be true. Okay, that is the definition of necessary conditions. And for the sufficient condition, we focus on these two. Okay, meaning that if Ss is true, then the statement S must be true. But if S is true, then this one has to happens, right? So example is the following. Says that we have two statements. The first statement says that a number can be divisible by 4, and the second statement B, is a number is even. Okay, so which is which? Okay. So if a number can be divisible by 4, then it must be even numbers, right? And if the number is even numbers, does that mean it can be divisible by 4? It doesn't necessarily. Yeah. Okay. So back to this graph.